Okay, so we have comparison of series, and basically there's going to be two different theorems. We're going to have theorem 9.12, and this is called the direct comparison test. It's also called I didn't leave myself enough room to write. Um, so the direct comparison test says we're going to let 0 be less than a sub n, less than or equal to b sub n for all n. All right, this means that between 0 and b, you should have an a, like a separate point. Kind of goes back to like sandwich theorem, that type of idea, where you just have that middle term. But we have two different parts to this. Part one is if the summation of n equals 1 to infinity of b sub n converges, then the summation of n equals 1 to infinity of a sub n converges.
So we have to like use the stuff we learned before spring break to do that.
Yeah. Which I think this is going to make more sense because I want to say yes, but also no. You'll see what I mean in a second. Like, yes, do you need to use it? But does it make is some of this simpler than doing that? Yes. So if the summation of n equals 1 to infinity of a sub n diverges, then you guessed it, the summation of n equals 1 to infinity of b sub n also diverges. Okay. So the reason I say that this might be easier in some aspects is because if you look at examples, you're going to split, and really you just need to determine one of them. If you determine one of them, then you know both of them. So you're not having to do a ton of extra work or anything like that. You're literally just trying to determine one series.
Can you move the page up?
Yeah, yeah. Is that better?
Yeah.
Okay. So I'll give you all a second to make sure that's written down, then I'll go from there. Am I good to move on?
No.
Okay.
No.
All right. So the idea is here that if a larger series converges, then the smaller series also converges. If the smaller series diverges, then the larger series also diverges. So that's why they go hand in hand. And if you need to see that type of statement, it's down at the bottom of the page 617. It'll be the second page in what I post on Classroom for y'all. Because that might help it make more sense than just thinking about it in terms of inequalities and then just seeing it written down, where it's more just worded out for you. And what we're going to do is we're going to end up splitting fractions today, is kind of what's going to happen. Ready for an example?
Good.
Okay.
Doesn't say I'm ready.
Okay, cool. So the examples that we're doing today are all fraction based like they were before. And we just want to determine the convergence or divergence of the summation n equals 1 to infinity of 1 over 2 plus 3 to the nth power. When you have something like this, come on, focus up, Kummer. What you're going to do is you're going to split off the value here, and we're going to really look at it as this series resembles the series of n equals 1 to infinity of 1 over 3 to the nth power.
So you're just taking the part that has the n.
Right. And the reason we want to do this is because then we have two different things. We have an a sub n and a b sub n. So we have a sub n is equal to 1 over 2 plus 3 over n. When your denominator is larger, that's a smaller number, so it's less than 1 over 3 sub n, which is equal to b sub n. And we know that n is greater than or equal to 1. There's actually a graph in the textbook in that I've linked to you guys. It's next to this example. And you can tell that they're both going, like they're both converging to the same area. And it's because it's a geometric series. So you go back, and if you, like, it's been a while since, because of spring break, you go back and look at geometric series, and you're like, oh, hey. And then you follow that rule. So since one converges, they both converge. So converges. So this is using those properties before, but when you see something kind of weird that we didn't see before, you just make it into what we had seen and then be able to solve it.
Okay.
Does that make some sense? Like we're really trying to relate this back to what we learned before and splitting it off into something we have seen, and then using what we know about this to show that they both converge. And again, if the larger series converges, so if this one converges, then the smaller series converges. If the smaller series diverges, then the larger series diverges. Like they go hand in hand. So really, you're only solving the one that you know from before.
Yeah, that makes sense.
Okay. Okay. So let me talk about limit comparison test as well. So then you have theorem 9.13, and this is the limit comparison test. And with the limit comparison test, things have slightly changed. If your a sub n is greater than 0 and your b sub n is greater than 0, and the limit as n approaches infinity, a sub n over b sub n equals a limit.
Oh my gosh.
Yeah, I know. Where L is finite and positive, then the summation as n equals 1 to infinity a sub n, and the summation as n equals 1 to infinity of b sub n either both converge or diverge. Wow, I really had to like fit that in. I don't remember us using this a lot in Cal 2 last year. There's actually some pretty good examples in the textbook of different things that are happening, and they actually do a cool little chart on the top of the 4th page where it says like the given series, it shows their comparison test, and then it shows the conclusion. So that might be useful to look at over time just because it gives you a nice little detail of everything that's going to happen. We're going to look at an example, but that might help with some clarity of how we got what we got. So the idea is here, whenever we have a given series, we're going to take the highest powers in the numerator and denominator and work from there. And we're going to multiply them back in. So hopefully that will help a little bit, and we'll see it in just a second. I'll let y'all get that written down. And y'all just let me know when we're good to move on.
We're good.
Okay.
I'm good.
Same here.
So, since we're a little bit short on time, and I want to be able to ask questions and stuff. Example, and it's the same idea of determine convergence or divergence of, and this time you get this n equals 1 to infinity summation of n times 2 to the n all over 4n cubed plus 1. Okay, you're going to look at these functions that you get. And the best way to make a reasonable comparison, and I'm going to separate this out for a second, and right here I want to write the fact of this needs to be 2 to the n over, well, do I want to write that? No. In Memento. I won't write that right now. You want to separate these out by the highest powers in the numerator and denominator. Now, obviously, you have a two-part problem here where you have an n and then 2 to the n, and your highest power in the denominator is 4n cubed. So I want to separate this out and think about this as... Sorry. Really, you're just separating out the highest powered n's. So this is n cubed. But we need to realize that these kind of go away. Sorry, and I want to write implies, not that they're the same. So you end up with 2n over n squared. Because you have two different issues here. Like you have an n to a power of 1, but you also have a constant to a power of n. So both things carry over for your implication. And then here you bring n cubed out, because that's your highest power n. And then these would cancel, obviously. So you have 2n over n squared. So your in this case, your reasonable comparison.
Is this gonna be a longer example?
Kind
of the same as the last one.
It's slightly longer than the last one.
Okay.
So if you want to wait a second, and then you can see.
Okay, yeah.
That might be a good idea. All right. So automatically, this series diverges due to nth term test. All right, let's say you don't remember that. So then you have to do some work and then realize what the interp test is. Um, Okay, and we get that from the limit. And you do limit as n approaches infinity of a sub n over b sub n. Oops, it's supposed to be b sub n, and that's supposed to be 8. All right, I get it.
Whoa.
Didn't want to write any of that. That's fine. A sub n, b sub n. So we get limit as n approaches infinity. And we have this idea of we keep the original, so the n, 2 sub n, 4n cubed plus 1, and then we write what we found as our comparison, which is n squared over, or we flip it, sorry, of 2 sub n, because it's division. And when you do that, you're left with the limit as n approaches infinity of n cubed over 4n cubed plus 1. And then if you remember the rules, if the powers are the same, you take their leading coefficients and you get 1/4. And when you get a fraction, it diverges. So
Okay, can you move it up? So
yeah,
I
sorry.
can read? No, it's fine.
There. Is that better?
Yeah.
I'm going to stop that recording there.